very firstly as as it is called as bimolecular displacement reaction, bimolecular displacement reaction, which is also called as addition elimination reaction. And second type of reactions which we are going to see is known as elimination addition reaction, which is also called as benzene reaction. We'll go into the details of all this. What we are going to focus is especially these two kinds of reactions under the heading of your NASR. Now coming to the same point, why I can't, if I'm unable to convert this alkyl halide into the phenol, how I'm going to convert this alkyl halide into the phenol. This alkyl halide into the phenol, then definitely my nucleophile here has to be OH minus, and this is converted into the phenol only when this aryl halide is capable of undergoing this reaction. But this particular reaction proceeds very slowly, and ideally this particular reaction is not possible. But at the same time, it is observed that when these rings have been replaced, or when these rings have additional electron withdrawing group present, then these rings can undergo nucleophilic aromatic substitution reactions very easily. What do I mean to say is, when I am considering chlorobenzene and when the reaction is taking place with nucleophile OH minus to give me a phenol, the reaction sounds to be difficult. But the moment I introduce one or the other electron withdrawing groups, and when I convert my simple aryl halide into this particular category, and when I make this react with a nucleophile, then definitely this will be able to give me the product comparatively easily, and that product is nothing but paranitrophenol. So now if I look at this reaction, I can understand that yes, the Cl is replaced with the hydroxy group, so it is going to be a substitution reaction. And since this is nucleophile which I am using, it is nothing but your nucleophilic aromatic substitution reaction. What at the time you just everyone accept that when I am having this electron withdrawing group present, then and then only this particular reaction is possible, and this particular reaction is an example of your first category, that is bimolecular displacement reaction or addition elimination reaction. Whereas this particular reaction where you have your chlorobenzene reacting with the nucleophile, this particular reaction is an example of your elimination addition reaction or the benzene mechanism. Okay, when I have one of the electron withdrawing group present, I am repeating, when I have one or the other electron withdrawing group present, that particular reaction is falling into the example of bimolecular displacement reaction, and when I have only aryl halide, this particular reaction is falling into the category of elimination addition reaction. Now here I have written a paranitrochlorobenzene. I may even have an example of orthonitrochlorobenzene reacting with the nucleophile and giving me product on the similar line where Cl is replaced by OH group. So here, to conclude for this particular point, what I am trying to convey is, when I am considering nucleophilic aromatic substitution reaction, as it has already been discussed, they are not so easy to perform. First thing. Second thing, definitely their mechanism is different than that of your SN1 and SN2, because if I consider SN2, you all know that there has to be a backside attack, right? There has to be a backside attack. If I consider here that this is getting replaced by the OH, that backside attack is not absolutely possible, because you have an pi electron rich system. If you remember, in case of SN2, there has to be a pentavalent carbon which has to be formed. Here all those scopes are absolutely nil, and thus SN2 mechanism is not possible. What about SN1 mechanism? In case of SN1 mechanism, you all know that it is a two-step mechanism, and in the first step you have a formation of carbocation. I hope you remember this. When we talk about SN1 mechanism, what you have is CH3 unit, and this is your Cl. So in the first step, what happens is this Cl departs and it generates a carbocation. Now if similar kind of a mechanism, if I would try to extrapolate it to chlorobenzene, what will happen is this Cl has to depart, and then what it will convert? It will be converted into a carbocation, which is really very difficult, and rather which is not possible. Thus we have seen that SN2 is not possible, we have seen SN1 is not possible. Okay, so this is the second point that we need to take a call, that though these reactions are possible, absolutely it involves altogether different mechanism. Okay, so if so, what is that mechanism that we will see? But before actually going into that mechanism, what we all have seen is there are two types which you have in nucleophilic aromatic substitution reaction. This is either bimolecular displacement reaction or elimination addition reaction. When you have bimolecular displacement reaction, it is also called as addition elimination type, and elimination addition reaction is also called as benzene reaction. Don't try to recollect all these terms at a stretch. What you can simply consider at this moment is, when I say NASR is divided into two different types. Yes, what you should remember is, I have these reactions possible with chlorobenzene alone. I have these reactions possible with substituted chlorobenzene. Chlorobenzene will give me elimination addition type of reaction. Substituted chlorobenzene will give me bimolecular displacement type of reaction. Okay, so in case of bimolecular displacement reaction, what I need is, or put it in another way, which all candidates will give me bimolecular displacement reaction? Number one, bimolecular displacement reaction will be given by substituted aryl halide. Here in this case, it is substituted chlorobenzene. First thing, I have to have a substituted aryl halide. So the first point which I am mentioning here is, I have to have a substituted aryl halide. Okay, now what about this substitution? This substitution has to be an electron withdrawing group. So for example, what we have seen is NO2. I have to have an electron withdrawing group. I have to have substituted aryl halide. Aryl halide can be, I may have Cl, I may have Br, I may have F, anything. But as you all know, Cl and the Br are the most reactive one. When I am considering electron withdrawing group, I may have NO2, I may have Cn, I may have COOH, CHO, all those groups which you all have already come across, which are electron withdrawing, any of it I can have. Third characteristic point which I have to have is the position of this electron withdrawing group. The position of this electron withdrawing group has to be either ortho or para, or both ortho and para. If and only if I have all these three conditions being fulfilled, then I can have nucleophilic aromatic substitution reaction, which is taking a path of bimolecular displacement, meaning when I have a nucleophilic aromatic substitution reaction, the candidate for that particular reaction has to be substituted aryl halide. That substitution has to be electron withdrawing group, and that electron withdrawing group should be present either ortho or para position.